A grounding electrode system is a critical component of a building's electrical system. Its primary purpose is to provide a low impedance path for fault current to return to the source, which helps to trip a circuit breaker or fuse and clear the fault. This, in turn, helps to protect people and equipment from electrical shock and fire hazards. The grounding electrode system also helps to stabilize the electrical potential of the building's metallic components, reducing the risk of voltage differences that could create a shock hazard. A grounding electrode is a conductor buried in the earth that establishes a connection to the earth. It's a vital part of the grounding electrode system. The National Electrical Code, or NEC, specifies the requirements for grounding electrode systems in Article 250. These requirements are designed to ensure that the system is effective in providing a safe and reliable path for fault current. The NEC defines a grounding electrode system as the interconnected grounding electrodes at a building or structure. This system can include a variety of electrodes, such as metal underground water pipes, metal in ground support structures, concrete encased electrodes, ground rings, and rod and pipe electrodes. Metal underground water pipe. A metal underground water pipe that is in direct contact with the earth for at least 10 feet and is electrically continuous is a common grounding electrode. The water pipe must be supplemented by an additional electrode, such as a ground rod or ground ring. Metal and ground support structure. Metal and ground support structures, such as pilings and caissons, can also be used as grounding electrodes if they are in direct contact with the earth for at least 10 feet. Concrete encased electrode. A concrete encased electrode, also known as a U for ground, is a steel reinforcing bar or rod that is encased in at least 2 inches of concrete and is in direct contact with the earth. It should be at least 20 feet long. Ground ring. A ground ring is a bare copper conductor that is buried in the earth in a circular shape around the building. It must be at least 20 feet long and buried at a depth of at least 2.5 feet. Rod and pipe electrodes. Rod and pipe electrodes are the most common type of grounding electrode. They are typically made of copper or steel and are driven into the earth. The NEC specifies the minimum length and diameter of rod and pipe electrodes, as well as the minimum spacing between them. The size of the grounding electrode conductor, or GEC, which connects the grounding electrode to the building's electrical system, is determined by the size of the service entrance conductors. Table 250.66 in the NEC provides guidance on selecting the appropriate size of the GEC. The grounding electrode conductor must be connected to the grounding electrode in a manner that provides a permanent and reliable connection. The NEC specifies the methods that can be used to make this connection. One example is exothermic welding. The grounding electrode system must be properly installed and maintained to ensure its effectiveness. Regular inspections should be conducted to check for corrosion or damage to the electrodes or conductors. The connections should be tightened periodically to ensure that they are secure. The resistance of the grounding electrode system should be measured to ensure that it is within acceptable limits. The NEC recommends that the resistance to ground should not exceed 25 ohms. If the resistance is higher than 25 ohms, an additional grounding electrode may be required. It's also important to note the requirements for bonding. Bonding refers to the connection of all metallic parts of a building's electrical system to the grounding electrode system. This includes metal conduits, metal enclosures, and metal piping systems. Bonding helps to ensure that all metallic parts are at the same electrical potential, reducing the risk of shock hazards. The NEC specifies the requirements for bonding in Article 250. In summary, a properly designed and installed grounding electrode system is essential for electrical safety. It provides a low impedance path for fault current, helps to stabilize the electrical potential of the building's metallic components, and reduces the risk of shock and fire hazards. The NEC provides detailed requirements for grounding electrode systems, and it is important to follow these requirements to ensure that the system is effective. Firstly, selecting the right type of grounding electrode depends on several factors, including soil conditions, the availability of suitable electrodes, and local regulations. Secondly, consider the soil resistivity. Soil resistivity is a measure of how well the soil conducts electricity. Low soil resistivity is desirable because it allows fault currents to flow more easily to ground. Soil resistivity can vary significantly depending on the type of soil, its moisture content, and its temperature. Soil testing should be performed to determine the soil resistivity at the site. Thirdly, the NEC specifies the minimum size and type of grounding electrodes that can be used. For example, a ground rod must be at least 8 feet long and 5/8 inch in diameter, unless it is listed for use in shorter lengths. Fourthly, the NEC also specifies the minimum size of the grounding electrode conductor. The size of the GEC is determined by the size of the service entrance conductors. The larger the service entrance conductors, the larger the GEC must be. Fifthly, the grounding electrode system must be installed in accordance with the NEC. This includes requirements for the depth of burial of the electrodes, the spacing between electrodes, and the methods used to connect the GEC to the electrodes. Sixthly, the grounding electrode system should be inspected and tested regularly to ensure that it is functioning properly. The resistance of the grounding electrode system should be measured to ensure that it is within acceptable limits. The NEC recommends that the resistance to ground should not exceed 25 ohms. Seventhly, it is important to coordinate the grounding electrode system with other grounding and bonding systems in the building. This includes the equipment grounding system, which provides a path for fault current from electrical equipment back to the source, and the bonding system, which connects all metallic parts of the building to the grounding electrode system. Eighthly, special attention should be paid to grounding electrode systems in areas with high lightning activity. Lightning can cause significant damage to electrical systems, and a properly designed grounding electrode system can help to protect against lightning strikes. Ninthly, grounding electrode systems should be designed and installed by qualified electricians or engineers who are familiar with the NEC requirements. They can ensure that the system is properly designed and installed, and that it meets all applicable codes and standards. Tenthly, it's essential to document the grounding electrode system. This includes keeping records of the types of electrodes used, their location, and the results of any testing that has been performed. This documentation can be helpful for future maintenance and troubleshooting. A critical point to consider is the use of supplemental grounding electrodes. While a metal underground water pipe is a common and effective grounding electrode, it must always be supplemented by an additional electrode. This is because water pipes can be subject to corrosion or disconnection, which could compromise the effectiveness of the grounding system. Common supplemental electrodes include ground rods, ground rings, and concrete encased electrodes. It is important to select the appropriate supplemental electrode based on the specific conditions of the site. Another important aspect is the connection of the grounding electrode conductor to the grounding electrode. The connection must be made in a manner that provides a permanent and reliable electrical connection. The NEC specifies the types of connectors that can be used for this purpose. Common connectors include exothermic wells, listed grounding clamps, and reversible compression connectors. The connection must be protected from corrosion and physical damage. In addition to the requirements in Article 250 of the NEC, there may be local codes or regulations that apply to grounding electrode systems. It is important to check with the local authority having jurisdiction to determine if there are any additional requirements. For example, some jurisdictions may require that the grounding electrode system be inspected and approved by a qualified inspector before the building is occupied. Proper maintenance of the grounding electrode system is also essential for ensuring its long-term effectiveness. The system should be inspected periodically to check for corrosion, damage, or loose connections. Any problems that are found should be corrected promptly. The resistance of the grounding electrode system should also be measured periodically to ensure that it is still within acceptable limits. If the resistance has increased significantly, it may be necessary to add additional grounding electrodes or to improve the existing connections. The grounding electrode system plays a crucial role in protecting people and equipment from electrical hazards. By understanding the requirements of the NEC and following proper installation and maintenance practices, it is possible to ensure that the grounding electrode system is effective in providing a safe and reliable path for fault current. The grounding electrode system also helps to minimize electrical noise and interference, which can be important for sensitive electronic equipment. A well-designed and installed grounding electrode system can improve the overall performance and reliability of the electrical system. Furthermore, it's important to understand the difference between grounding and bonding. Grounding connects the electrical system to the earth, while bonding connects all metallic parts of the system together. Both grounding and bonding are essential for electrical safety. Bonding helps to create a low impedance path for fault current, which allows the circuit breaker or fuse to trip quickly and clear the fault. Without proper bonding, fault current could flow through unintended paths, creating a shock hazard. The NEC provides detailed requirements for bonding in Article 250. These requirements cover a wide range of topics, including the size of the bonding conductors, the methods used to connect the bonding conductors, and the types of equipment that must be bonded. In addition to the requirements for grounding and bonding, the NEC also includes requirements for surge protection. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges caused by lightning or other transient events. SPD are typically installed at the service entrance of the building, as well as at individual pieces of equipment. The NEC specifies the types of SPD that can be used, as well as the installation requirements. It is important to select SPD that are appropriate for the specific application and to install them in accordance with the manufacturer's instructions. In conclusion, the grounding electrode system is a complex and critical part of a building's electrical system. It is essential to understand the requirements of the NEC and to follow proper installation and maintenance practices to ensure that the system is effective in providing a safe and reliable path for fault current. Proper grounding and bonding, along with surge protection, are all essential for protecting people and equipment from electrical hazards. The specific configuration of the grounding electrode system will depend on the size and type of building, the soil conditions, and the local regulations. It is always best to consult with a qualified electrician or engineer to ensure that the grounding electrode system is properly designed and installed.